Today is the second part of my talk, which is called Isotropy group of an LND of the polynomial algebra in 3 variables. This is joint work with Nikhilesh, but I decided to say nothing about isotropy group. So my main task for today is to have an explicit example of non-triangulazible locally nilpotent derivation of rank 2 and an explicit example of locally nilpotent derivation of rank 3. Let me start with reminding some facts and definitions from the previous part. So one of the main definitions for today talk is definition of rank. This is n minus quantity of variables which can be in the kernel of our locally nilpotent derivation. And I remind that we proceed with n equals to 3. We mentioned some theorems, some known theorems, such as Rentschler theorem, that every locally nilpotent derivation in polynomial algebra, on polynomial algebra in 2 variables is equivalent to a triangular one. Mainichi theorem, that if I have a locally nilpotent derivation on a polynomial algebra in 3 variables, then its kernel is isomorphic to polynomial algebra in 2 variables. And we proved some theorems. The first one is that D is triangularizable, so it can be done triangular by changing coordinates by an automorphism. If and only if there is a commuting LND of rank 1. The second theorem is that we can take a local slice H and we can consider a subalgebra in algebra B. B is my algebra in 3 variables. So subalgebra which is obtained by adding this local slice to the kernel. This is polynomial algebra in 1 variable over kernel. This variable is our local slice. And then C is a subalgebra of B, which is also isomorphic to polynomial ring in 3 variables. And restriction of D to this subalgebra is just replica of partial derivation. So it is a derivation of rank 1. And it's convenient to take H to be a minimal local slice, which means that we have that its image generates Plin's ideal. Plin's ideal is ideal in kernel, which is defined as ideal generated by image of D intersected by kernel of D. This a theorem, known theorem, not our, of course, that this ideal is always principal, and we can take H to be so. And theorem 3, that if we have D is a LND of our algebra in 3 variables, and we are interested if there is another LND E, which is which commutes with D. And these two derivations are non-equivalent. So kernel, oh, I'm sorry. So kernels are different. So this E exists if and only if there is a local slice H such that its image is a polynomial in one variable. So there is a variable of B which is in the kernel, and D of H, this is image of our local slice, so it belongs to the kernel, and this is a polynomial just in one variable. Okay, this is all what I need from the previous part. It seems that theorem 1 I even should not use. So we need theorem 2 and theorem 3.
Sergey, some questions. Okay, looks very nice. But firstly, I don't know how to translate into Russian the Plin's ideal. Do you know?
I don't know.
Есть вариант либо цоколь, либо плинтусный, либо цокольный. Что-то такое.
It seems that I hear цоколь. It looks familiar.
Okay, and the second question, this is a known result about this Plin's ideal, says that it is principal. This is for polynomials in 3 variables, or in which generality it holds?
No, just for 3 variables. It can be found, for example, in Freudenberg's book. Of course, I don't believe that all facts from Freudenberg's book are known, and today I would like to consider some facts from this book, but this is from the beginning of this book.
So in this case, the kernel is the algebra of polynomials in 2 variables, and this is some principal ideals inside of this algebra, right?
Yes.
I see.
Okay, let me proceed with some examples. This example was considered on the previous part. This is example due to Bess, and we consider just the following locally nilpotent derivation. X goes to 0, y goes to x, and z goes to 2y. It can be checked very easily that xz minus y square is in the kernel. Of course, x is in the kernel, and it can be easily proved that kernel of this locally nilpotent derivation is algebra in 2 variables, x and this xz minus y square. Of course, D is dB is triangular, and we see that there is at least one variable in our kernel. So this derivation either of rank 2 or of rank 1. Of course, it is non-zero, so its rank is not 0. So let us prove that it is of rank 2, not of rank 1. Okay, let us suppose that it's of rank 1. Then there are some new coordinates, x prime, y prime, z prime, such that our dB have the following form. But we can see that dB is irreducible. So the image is not contained in any principal ideal. So f should be constant. But then dB has a slice, but it can be easily see that it have not a slice, so this is of rank 2. We can construct.
And how do you see that the image is not contained in a principal ideal?
Oh, the image of y is x, the image of z is 2y, so there is no.
They are coprime. I see.
It can be considered the replica of this dB. I have said that this xz minus y square is in the kernel, and so we can consider Nagate's example dn, which is equal to this polynomial multiplied by dB, and we have said in the previous part that this dn is rank 2 derivation, which cannot be, which is not triangulable. But we set it by Shestakov-Umirbaev theorem. It is a rather complicated theorem, so let us more precisely prove that this is not triangulable derivation. Okay. Let us consider theorem 3. Theorem 3 said that there is a commuting local and nilpotent derivation if and only if there exists a polynomial h such that d from h is a polynomial in one variable. But for our derivation dn, we consider that I'm sorry, what was the idea? It is not irreducible. It is divisible by this guy. So if we have let me write something. If we have such h, that d from h is polynomial in one variable, then this d from h is equal to xz minus y square multiplied by something. So since all of this is polynomial in one variable, then this is polynomial in one variable. But we can see that this is irreducible polynomial, so it cannot be polynomial in one variable, and we can say that xz minus y square is not a variable because of if we try to consider a system of variables such that this is x prime, some y prime, and some z prime, then we can consider the Jacobian matrix of this x prime, y prime, z prime with respect to x, y, z. And it should be as follows. I don't know what is here, but partial derivations of x prime is just z minus y minus 2y and x. And of course, it cannot be constant because these three guys are without free term. So it's impossible. So this is not variable, and hence d from h cannot be polynomial in one variable. Then theorem 3 said that there is no e such that as follows. I'm sorry, I should use theorem 1. By theorem 1, what's that theorem 1? I'm sorry, let me see. Theorem 1 said that if there is a commuting LND of rank 1, then D is triangularizable, if and only if. So since there is no such E, then there is no such E of rank 1. And hence either Dn has not I'm sorry, why I had some troubles. Theorem 1. D is triangularizable if and only if there exists such E that E D equals to DE. I have proved that there is no commuting LND at all. So there is no of rank 1. It seems that it's rather strange. Either of rank 1, it's not the case. D is not Dn is not triangulable, and we have proved this fact. I'm sorry. It seems that there is a little mistake because there is no case that rank of this LND is 1. There is only case that it is not triangulable. Okay. Now we have an explicit example of non-triangulable derivation. But one can say that it is not very good example because it is not irreducible. We take it Dn is just replica of dB, and since this is true, we have such familiar case, and so it seems that we can't obtain examples of irreducible LNDs of rank 2, which are not triangulable by this construction. But let us consider one example of such LND. It is not so easy to prove, but we try. First of all, I would like to prove the following interesting lemma. Let us consider two locally nilpotent derivations. And these two locally nilpotent derivations of our algebra B such that they commute. And let us take sigma an element from the kernel of D. And let us consider the derivation of the form E plus sigma D. Then I state that this is an LND. Okay, let us prove this lemma. Since E is an LND, we can take such number L that E in power L from sigma is equal to 0. Let us consider a polynomial of f from B. Since D and E are locally nilpotent, we can consider K and M such that D in power K from F equals to 0 and E in power M from F equals to 0. And it can be checked that our derivation in power L plus L multiplied by K plus K plus M from this polynomial f equals to 0. Just rather explicit computation. If we consider this power, what is it? When we extract all brackets, then we obtain a lot of summands, and each summand have the following view, have the following form. This form is a power of E, a power of D, sigma D, then a power of E, one more power of D sigma E, and so on. If I prove that each summand from f equals to 0, then we prove that our derivation from f equal to 0. Okay, let us consider our summand. The idea is that all these can be moved to the right part. It can be here, it can be done here because D commutes with E and D commutes with sigma since sigma is from the kernel. Okay, then we apply this guy to F. If this power is big, then D in this power from F equals to 0. If this power is rather small, then other powers of E is big. Sum of powers of E is big, and then either E, the power of E, we can. Okay, let us consider the case when this power is less than k. Then we can say that sum of powers of E bigger than LP plus M, where P is this guy which is less than k. And then we move dp d to the left, and here we obtain the following form. And now this guy is equal to E in some power from sigma, then E in some power from sigma, and so on, and then E in some power from F. Maybe some powers are 0 if two sigma are near to each other. And since the sum of these powers is big, then one of these powers is big. So either one of these multiples is 0, or this multiple is 0. So we obtain 0 as a result. I don't want to have explicit there is explicit calculations in the slide, but it seems that it's not very convenient to follow all these formulas, so I go on. Just once more consider statement of this lemma. Now let us apply this lemma to very particular derivations. We have dn. This is xz minus y square multiplied by db, and dz, partial derivation from. I remind that dB is triangular, and hence it commutes with dz. So in our lemma, this is sigma, this is d, and this is e. And hence we obtain a locally nilpotent derivation. Now I state that this locally nilpotent derivation is a locally nilpotent derivation of rank 2, and it is not triangulable. Okay, we have proved that this is
one comment. D of y, shouldn't it be xz minus y square into x, or just xz minus y square? D of y.
D of y. Yes, it should be
xz minus y square
multiplied by x.
x.
Yeah, you're right. I'm sorry. Here is x. I hope it is not very important. Okay, we compute that this is d of y is this, and d of z is this, just applying both parts. And hence d is irreducible, because these two polynomials are coprime. Okay, now we have an irreducible derivation, locally nilpotent derivation, and we are going to prove that it is not triangulable. First of all, let us set that d from sigma. I remind that sigma is xz minus y squared. D of sigma is x. It's just explicit computation. It's can be done in 1 minute, and we can prove that kernel of this d is k of xp, where p is as follows. Of course, x goes to 0. D from x, x0. This is true since db from x is 0 and dz from x is 0. Now let us consider d from p. This is d from sigma square minus 2y. Applying d from sigma, we have x, and hence this is 2 sigma multiplied by x. Applying d to minus 2y, this part from y equals to 0. Hence, we apply just the first part to y, and we obtain that y goes to x sigma, and hence minus 2y goes to minus 2 sigma x, and this is 0. So we computed. Of course, we should compute. We should prove that this is all the kernel, but our kernel should be of transcendence degree 2, and this algebra is algebraically closed. Hence, this is all the kernel, and let us prove that our derivation is of rank 2. Okay, suppose that it's of rank 1. Then there exists two variables in the kernel, and kernel is k of xp. Okay, then one of these variables can be done x, and another variable is f of xp, which is not lambda x plus mu. And let us prove that it cannot be a coordinate. We consider the Jacobian matrix. The first coordinate is x, so Jacobian matrix have the first row 1, 0, 0. And since we have the second coordinate f from xp, I'm sorry. Then we have explicit calculations say that how to give partial derivation of this f by y. This is partial derivation of x of f by x1, the first argument, multiplied by partial derivation of x by y, but this is 0, and partial derivation of x f by the second argument in point xp multiplied by partial derivation of p by y. This is as follows. And in similar way, we obtain partial derivation of this polynomial by z. This is as follows, and we can obtain a contradiction by some considering of polynomials, putting y equals to 0. We have that this and this divides all this polynomial, and multiplying and if we put y equals to 0, we don't obtain this cannot be 0, and so this partial derivation is just constant, and hence we put x equals to 0 and obtain a contradiction. It's not very interesting, but this is just explicit calculations which prove that our derivation in this example, this derivation is of rank 2. We need it in the following. We can't prove that this is not triangulazible now, so we need some preparations. Now let us proceed with some lemmas. Okay, lemma, let D be an irreducible locally nilpotent derivation of rank not bigger than 2. Let U be a variable in its kernel. Since our rank is not bigger than 2, then there exists at least one variable in our kernel. Then there exists a G in B such that D from G is equal to polynomial from U. This is rather similar to theorem 3. Maybe I should look to theorem 3 once more. It is in some sense the invitation of, I'm sorry, not invitation, invertible assertion for theorem 3, but so theorem 3 says that if we have such E, then we have such E if and only if we have such H that D from H equals to U. And what said our lemma that if D is of rank not bigger than 2 and it is irreducible, then we always have such F, and so we always have such E. Okay, let us prove this lemma. Since U is a coordinate, we can consider the system of coordinates which contain U. So B is equal to K of U V W. And now we consider, since D from U is equal to 0, we can consider D as a local nilpotent derivation of this algebra. We can add U to our field. Okay, this is irreducible local nilpotent derivation of polynomial algebra in 2 variables. Then it have a slice, and this slice have the form. It is from here, so this is polynomial G from U V W divided by polynomial from U. And since D from this guy is equal to 1, and the denominator is in the kernel, we can multiply this equation to the denominator and obtain D from G is equal to F. Okay, we proved this lemma, and with theorem 3, we proved that if we have an irreducible local nilpotent derivation of rank not bigger than 2, then there is commuting 1. The same statement what I have said just now in some reformulation, that if D is irreducible and there is no such U and such G, then rank of D is equal to 3. And a very interesting corollary is that if we have rank 2 derivation and we have 2 different systems such that one of variables are in the kernel. So we have 2 variables in the kernel. It seems that it's impossible because rank 2 derivation said that there is only one variable in the kernel, but there is only one variable in one system. But if I have 2 different systems, I have 2 different variables from the kernel. And a priori, it can be not connected between each other. But this corollary said that our coordinates are linearly dependent. So U prime equals to lambda U plus mu, where lambda and mu is from our field. So it means that algebra K from U equals to algebra K from U prime. I would like to say that for rank 1, for example, this derivation, partial derivation, of course, very many system of polynomial system of coordinates. One of the system is x, y, z, but I can take x plus y, x minus y, z. I can have more complicated system of variables. So it is not true that if I have a variable x, then in every other system I have variable lambda x plus mu. Okay, let us prove. We can assume that D is irreducible because we are interested only in its kernel, and every locally nilpotent derivation is proportional to a irreducible one, and so let us take this irreducible one. By the previous lemma, we said that since we have irreducible locally nilpotent derivation of rank 2, we have such G that D from G is F from U. And applying it to the other system, we have such G prime that D from G prime is H from U prime. But the Plin's ideal, as we said, is principal. Therefore, there is its generation, its generator T, such that it generated this Plin's ideal, but F from U and H from U prime belongs to this Plin's ideal because they are from the kernel and they are from the image. Hence, T divides F from U and T divides H from U prime. And hence, since T divides polynomial in one variable, then T is a polynomial in this one variable. So T is a polynomial from U. From the other hand, T is a polynomial from U prime. So either T is a constant or U prime is lambda U plus mu, because they are both irreducible. If T is a constant, then we have a slice and a rank of D is equal to 1, but we said that rank of D is equal to 2, so we have only the second case such that these two variables are almost the same. Okay, now we can proceed with our example. We return to our example such that this is sum of dB multiplied by sigma plus partial deviation from Z. I remind that D from sigma is equals to X, and sigma is XZ minus Y squared. And our goal is to prove that D is not triangulable. Suppose that D is triangulable. Then there is a system X tilde, Y tilde, Z tilde, such that it is triangular in these coordinates. So dx tilde equals to 0, dy tilde equals to f from x, and z tilde equals to g from x tilde y tilde. but x tilde is a coordinate in our kernel, since this is true and x tilde is coordinate. But x, I remind that d from x is equal to 0. And hence, we have two coordinates in our kernel. We have proved that d is not of rank 1, so d is of rank 2. And hence, we can apply our lemma and our corollaries. By corollary 2, we obtain that x tilde is equal to lambda x plus mu. And we can assume that x tilde just equal to x, because I can swap x tilde to x in this system of coordinates, and it should be also system of coordinates in which d is triangular. Then in this system, we can see that y tilde is a minimal local slice, but sigma is also a minimal local slice. Then these two minimal local slices are, I'm sorry, here should be a coefficient of proportionality which belongs to k star. But we can remind, I write that we can assume, we can change y tilde to a proportional one and assume that y tilde is equal to sigma plus an element from the kernel, and element from the kernel is a polynomial from x and p. I remind that p is as follows. And now we also consider the Jacobian matrix, and also by some consideration we have a contradiction. It seems rather boring, so I just skip it. But since we have a contradiction, then we obtain that d is not triangulable. We have proved that d is of rank 2, d is irreducible, so we obtain an irreducible non-triangulable local nilpotent derivation. Okay, and this was let me say a conjecture. I don't remember, Nikhilesh. In some way, it seems to me sometimes that we have proved this conjecture, but I have not found. So it seems that it's still conjecture. Conjecture that every local nilpotent derivation of rank 2 can be obtained by this construction. We have triangulable d, just triangle one, multiplied it by sigma from, I have not read, sigma should be from the kernel. And add a rank 1 derivation which commutes with this d. It seems to me that it's very similar to true that all local nilpotent derivation of rank 2 can be obtained by this construction. And now let us go to rank 3 derivations. for this rank 3 derivations, situation is very complicated, and I have a lot of good ideas, but let me start with just the following 2 slides, just summary of Freudenberg's book. And he gives an example of rank 3 derivation, and it's just mysterious one, but the proof that this is derivation is of rank 3 is not very complicated. We can prove it. Let us consider algebra in 3 variables, x, y, z, and let us consider these 3 polynomials. At the beginning, we need the first 2 polynomials, f and g. And let us consider the Jacobian derivation of with respect to these 2 polynomials. I remind that Jacobian derivation is as follows. We have d from a polynomial f is just denominator of Jacobian matrix, such that here df dx and so on, dg dx and so on, and df small dx and so on. This Jacobian derivation is always a derivation, but not always a locally nilpotent. But Freudenberg said that it's easily can be checked that all as follows. I have not checked, of course. I believe it, but it looks very. I don't know from where it can be. How can one? How can we to find this derivation from where? I don't know. Okay, sorry for my English. Okay, let us prove that this is a local and nilpotent derivation of rank 3. This is proven is due to Freudenberg's book. We can see, and it seems that this is a result due to Freudenberg. Consider Z gradient. Just a very standard gradient that degrees of all variables are equal to 1. Then it's really easy to check that f and g are homogeneous. F is homogeneous of degree 2, and g is homogeneous of degree 5. And then our derivation d is also homogeneous of derivation 2 plus 5 minus 3 equals to 4. Let me explain why 2 plus 5 minus 3. When we have this Jacobian matrix, then f is of degree 2, g is of degree 5, and each partial derivation, since degree of each variable is equal to 1, each partial derivation give us minus 1. So we have minus 3, and this is 4. This is just a rather known fact that if we have homogeneous polynomials, then Jacobian derivation is also homogeneous with this degree. Okay. Occasionally, we should remind dB, our best example. And this is f, this is in our previous notation is sigma, and kernel of this dB is equal to k of xf. And then let us consider the intersection of kernel of D and kernel of dB. Of course, these two polynomials f and g belongs to the kernel of D. And hence, in this intersection, at least there is k of f. But some technique which is very similar to our previous part, that intersection of two local nilpotent derivations is if they are not coincide, and these two local nilpotent derivations in our algebra in three variables. It is just a polynomial in one variable where f is where this variable is a variable of each kernel, not of all the algebra, but of each kernel. And hence, this intersection is a polynomial in one variable, but f belongs to this intersection, then it coincides with k of f, and we have that kernel of D is polynomial in two variables, f and one more variable, and this one more variable can be taken homogeneous. But G big is in the kernel, and G big is of power 5. This is f of power 5, f is of power 2, and G big should be belongs to this subalgebra. This follows that either degree of G is equal to 1 or degree of G is equal to 5. Because otherwise, the only one case where we can construct 5 not from these two guys is degree G is equal to 3, but then G is polynomial in f multiplied by G, not polynomial, but just constant multiplied by f multiplied by G, but G big is irreducible, so it cannot be f multiplied by G, so G can be either of power 1 or of power 5. But of power 1, it cannot be, because if degree G is 1, then what monomials of power 5 we have? F square multiplied by G, F multiplied by G cubed, and G in power 5. All these monomials is divisible by G small. So then G big is divisible by G small, and it is not irreducible. But since G big is irreducible, we have that sorry, we have that degree of G small is equal to 5. And then we can assume that it is equal to G big. Hence, we can say that kernel of D is equal to K of Fg. And since it is so, f if of degree 2 and g is of degree 5, we have no elements of degree 1 in our kernel. But if u is a coordinate in our kernel, and we have a coordinate in our kernel if rank of d is not equal to 3, then you should have a linear part. Otherwise, it cannot be taken into system of coordinates by the previous arguments with Jacobian matrix. So u is equal to u1 plus something, where u1 is of degree 1. And since d is equal to 0 from u, then and d is homogeneous, then from each homogeneous part, it equals to 0. So d from u1 equals to 0. u1 is not 0, and we obtain a polynomial of degree 1 in our kernel. And so we have a contradiction because there is no polynomials of degree 1 in our kernel, and there is a polynomial of degree 1 in our kernel. Hence, what we assume is false, and we assume that there is a coordinate of in our kernel. So we assumed that rank of d is not 3. Hence, rank of d is 3. For me, it's awful because we have very strange situation. We have these polynomials, and I don't understand from where these polynomials have taken. And then we have such checking and so on. I can't say that I know the way to not have deal with such polynomials, but in some sense, I have an explanation of this example. Let us proceed with this explanation. Okay, we have these 3 polynomials. This the last polynomial is just can be computed that this is local slice of our derivation, and d from r is equal to minus fg. R is a minimal local slice of d. And then, as in our theorem 2, let me remind, sorry, this is theorem 2. We said that for every locally nilpotent derivation, we have this local slice, minimal local slice, and then we have this subalgebra C, such that D restricted to this C is rank 1 derivation. Okay, let us do by the same way. Let us consider K of FGR. FG is just our kernel, and R is our local slice. So this is polynomial in variable of local slice over our kernel. Okay, let us consider a restriction of our derivation to this subalgebra C. And since d from r is equal to minus fg, we just obtain this very simple derivation of rank 1 delta equals to minus fg multiplied by partial derivation from r in this subalgebra. Okay, let us apply our theory to check that our D is of rank 3. Oh, I'm sorry, I can't erase this. Okay, let us apply our theorem. Suppose that D is not of rank 3, then there is a commuting LND. Okay, suppose that there is a commuting LND E with our D. Then it can be checked that C is E invariant. Because what we can say about applying E to C? Kernel of D is E invariant because they are commute. The image of local slice R by E is a local slice of our derivation D. But all local slices are proportional, and one local slice can be obtained by another by multiplying to a scalar and adding something from the kernel. This implies that our subalgebra C is E invariant. And the restriction E to C is a local and nilpotent derivation with this delta, which is a restriction of D to C. Now let us consider our delta. Delta is minus Fg multiplied by partial derivation. Delta is reducible. And we apply our theorems. Okay, let me proceed just by the text. If I have a polynomial P, then when I apply delta to P, then this image is divisible by Fg because delta has the following form. Therefore, there is no such polynomial that its image is polynomial in one variable, because each image is divisible by Fg. F and G are algebraically independent, and we have no polynomial in one variable which is divisible by F multiplied by G, because just otherwise F and G is polynomial in this U, and this is a contradiction. Okay. Since we have not such such polynomial in the image, by our theorem 3, we said that there is no commuting LNDs on C which are commute with delta. There is no non-equivalent commuting LNDs. And hence our restriction of E is equivalent to our restriction of D, and hence the kernels coincide. But kernel of delta is just kernel of D. This is F of K of Fg. So kernel of E is equal to kernel of D. And then we obtain then there is no commuting LNDs with our D, which are not proportional. And hence, by our corollary 2, if D is irreducible, then its rank is 3. Let me remind corollary. Sorry. Corollary 1. If D is irreducible, then if there is no such polynomial in image, then a rank of D is equal to 3. Okay, the only what we should check in this proof is that D is irreducible. But this is some kind of explicit computation. This polynomial f, r, and g are given in such a way that x, y, and z can be obtained by these formulas. It is not a coincidence, because we know that for our local nilpotent derivation, if we have localization by image of local slice, then when we add it to k x, y, z, and when we add it to k of f, g, r, I'm sorry, let me put it down, that kernel of D of H, our C. So C from one localization from image of local slice is equal to all polynomial ring localization by the same. Hence, x, y, and z is from this algebra, and hence it is they are from this algebra, and there should be some formulas with denominator proportional to some power of fg, such that x is a polynomial in fgr divided by some power of this guy, and y and z as follows. So we can check that our derivation is irreducible. We should not check that D is locally nilpotent, because we know that this delta is locally nilpotent, and it follows from this that that D is also locally nilpotent. And let me try to summarize. Okay, we have given another proof of that this locally nilpotent derivation is of rank 3. Let us summarize all this and try to explain how can we try to obtain new examples. Because what is the problem of this example? From one hand, I don't understand how to take this f, g, and r, but this is the problem which is rather difficult. I don't know on any procedure how to obtain this triple. But from the other hand, the previous proof is it use that D is homogeneous, but that only few derivations are homogeneous. So we would like to construct a lot of examples, and most of them should not be homogeneous. And the second proof is a technique how can be proved that a locally nilpotent derivation is of rank 3 without using homogeneity. Okay, let us summarize. Here some computations. It's not interesting. The last slide. is our thought about how to obtain similar examples. We need the following data. We need three polynomials, f, g, and r, which are polynomials in k of x, y, z, such that they belongs, we can invertibly represent x as a polynomial in f, g, r, but polynomial in f, g, r is a proper subalgebra, but we use 1 divided by some polynomial p in first two, in f and g. I don't know a good way how to obtain this situation. And this polynomial p should be rather bad. Let me proceed and explain what is rather bad. We consider local and nilpotent derivation of rank 1 in this subalgebra k of f, g, r, which is given by this formula. This is just partial derivation, which multiplied by an element from its kernel, so it's a locally nilpotent derivation. And this locally nilpotent derivation is not irreducible. And for not irreducible derivations, often, if p is rather bad, we can check that in image there is no polynomials in one variable, which is variable of k, x, y, z. For example, if p is multiplication of two multiples as in the previous example, we can prove that there is no polynomials in image in one variable. And hence, there is no commuting LNDs with this delta on this C. And hence, if we extend this delta to k of x, y, z, it can be extended because this polynomial is in the kernel. Hence, we can apply our derivation to x, y, z and obtain elements from x, y, z. It's not if, it's it. It should be LND because delta is LND, and extension of LND in such way should be LND. What we need is that this is an irreducible one. This is the second problem, how to prepare all our data in such a way that D should be irreducible. In some sense, it means that P is not too big, because if P is too big, then delta is not irreducible, and going to our extension, it should be also not irreducible. But if we managed to deal all of this, we obtain an LND D of our algebra, and it should have rank 3 because there is no commuting LNDs within. Unfortunately, this is just some thoughts, not an algorithm how to obtain plenty of examples, but as an idea, we can just a little bit modificate this data which is obtained from Freudenmuth's example. For example, in Freudenmuth's example, we have where it is f equals to xz minus y square, and r is given by x cubed plus yf. From this, we can this g is not random. It is given in such a way that x, y, z is given by these formulas. We can take x the same, f is the same, and r is a little bit different. Here is square, not cube. And for I'm sorry, here's should be partial derivation from r. We can consider the same partial derivation. Here's something strange. Delta should be minus fg multiplied by partial derivation on r. We can construct g, we can construct formulas to x, y, z, which give it in such a way, and we can obtain a new example of rank 3 derivation which is not homogeneous. Unfortunately, I have not better ideas, but it seems that by modification of this data, we can construct a lot of examples. Of course, it would be very pleasant to have some construction of this FGR. I don't know, which is not modification of data from Freudenmuth's example. Okay, it seems that all for today. I have not say something about isotropy group. We have some results about it. I don't know. It seems that it's not so interesting. If you want, I can proceed in one more time, but it seems that it can be finished in such a way.
Okay, many thanks to Sergey. Dear colleagues, any questions, comments? If not, then let us think that everything was explained very clearly and in details. In my opinion, this is a very interesting work, and I will wait for a text. I think it definitely deserves publication, so I recommend you to. Do you have already some text?
We have text about part of this and some more results in isotropy group, but some results are not in the text yet.
Okay, so if there are no questions or comments, Nikhilesh, maybe something from your side? No?
No, it's fine. Well, we are still working on this construction, what Sergey mentioned, and we can hope to write it down once we finish it, hopefully. I have just a comment, but I don't know whether it's the point which Sergey said regarding that choosing of f and g in the Freudenmuth's example. How did you got hold of such polynomials? They come from something called as local slice constructions. That is not a very, I will say, an easy technique. It's an involved technique. It's given in this book. but maybe we can look more into it and see how naturally it comes out to get more. These are called as examples of Fibonacci type. So there are, but it generates positive homogeneous LNDs, the way he creates. So if we go for non-homogeneous ones, we have to think out of the box, probably.
Okay.
Okay,
So
thank
am I
you.
right that there are constructions which give some examples of locally nilpotent derivations of rank 3?
Yes, yes.
And all these derivations are homogeneous, and maybe we can use the data from these examples to construct new non-homogeneous.
Yes, we can look into that always.
Okay, thank you so, Sergey.